Okay, in this video we're going to talk about the basic ideas behind systems. We'll first talk about some very simple systems that the operations they perform in the input signal to produce an output are quite simple and straightforward. We're then going to talk about how you can hook systems together to make more complicated input-output relationships, the relationship between the input and the output. And then finally, we're going to talk about linear systems, and then time invariant systems. And the ones that are both linear and time invariant are going to be extremely important to us, as we're going to see. All right, so let's talk about some simple systems, ones that are pretty easy to understand. And the first one is quite simple. It's called a gain. And what this system does is the output is equal to the input times a gain, a number g, a scalar. So I think that's pretty easy to understand. It just takes the input, multiplies it times a number, and that's its output. So you can use the unit step as a example input to see how this works. So the input here, as I've drawn it, is a unit step. And then the output is the same unit step, except it's now got an amplitude of g instead of 1, whatever that is. This special case that I've indicated here of an amplifier has to do with the fact that if g is bigger than 1, the terminology is that it is an amplifier. It makes things bigger. It amplifies. There are cases in which g is less than 1, in which case it serves as an attenuator. It makes things smaller. And finally, a somewhat confusing terminology, if g is negative, it's called an inverter. So it does not mean take the reciprocal. So if we use our unit step input, for example, here, so we bring in a unit step, and we look at what the output's going to be. If g was negative, the output would be like that. So it doesn't mean take the reciprocal, it means change the sign. I don't know where the terminology inverter came from, but that's what it is. Okay, let's talk about some more systems. And this one we've seen already. The time delay. The output is equal to the input a little bit later. It's been delayed. And again, using the unit step as our example, you delay, the output is also a unit step, but it's now delayed. We've seen this, like I said, already in talking about signals. Pretty easy to understand what it does. Turns out it's a bit more complicated to build. So delay boxes turn out to not be easy. We do want to point out that they do occur naturally. Light, in fact, all electrical signals travel at a finite speed. They don't travel from one place to another instantly. So if something happens at the sun, a change in the brightness of the sun, it won't reach the Earth for about 8.5 minutes. So that's a delay. So that's a physical delay. Just running an electrical signal through a long piece of wire introduces a delay. So in some cases it's pretty easy. It's very hard to have a controllable delay, though. That could be a bit more complicated. So, like I said last time, if you have tau greater than 0, that's called a time delay. If tau is negative, it's a time advance. It occurs earlier in time. Turns out such systems are pretty hard to build because, again, using our unit step as an example, if tau were negative, the output would come out before the change in the input occurred. So if this is, for example, at -1, this output at time -1 is going to have to occur before it occurs at the input. So somehow the system would have to know the future value, the future behavior of the input signal. That's a little weird. And so time advances are great mathematical things, but building them is more than just a little complicated. I have another example that's along similar lines, something that's easy to write but hard to build, and that's called time reversal. So here, using our unit step input, you put in the unit step, and it comes out delayed. Not delayed, I'm sorry. Mistake, it comes out time reversed. So notice that again, the value at, let's say, time -1 is going to be the value of the input at time 1. The system would have to know what was going to happen 2 seconds ahead, in that case, to produce an output. Well, it gets even worse. What happened at time 10 would have to come out at the output at time -10, which means it would have to be able to predict way ahead in the future. In fact, predict the entire waveform into the infinite future and then put it out at the infinite past. So time reverse systems are very weird, very hard to build. However, they have a very simple mathematical description. Not all simple systems can be built. Well, let's talk about some systems that are maybe not so simple, but easy to understand, and that's the derivative system. So what this system does is simply take the input and evaluate its derivative, and that produces the output. So easy to understand, and actually derivative systems are actually easy to build. We can also talk about systems that integrate, and I want to point out something about this. Again, these are easy to build, but there's a convention in this course that's important. And that is, there are no such things as indefinite intervals in this course. Every integral is a definite integral. And most of our integrals will start at -infinity and go up to time t. I tend to use Greek letters for variables of integration. It's just a convention I have to make it clear that it is a variable of integration. This will come up pretty frequently. So the output y is equal to the integral over all previous time of the input x. And like I said, there is no trouble building this system. Okay, those are our simple systems. Let's put them together. So let's talk about some simple structures. Perhaps the simplest is called the cascade structure. And essentially, all it has is one system after another. We've already seen this in the fundamental model of communication. It is a cascade of several systems, in fact 5 of them. So the input to the entire chain is x, goes through S1, produces W, and then W in turn produces Y. So we can think about this as one system which is constructed as a cascade of 2 simpler systems. And in fact, that's exactly what cascade structures are for. For example, suppose you wanted a system that delayed and inverted. Well, I could do that by building an inverter, let's say here, and then passing that, the output of the inverter, into a delay. And then the overall relationship between x and y would be an inverted delay. So that's the way you get something a bit more complicated from simpler systems. Another way you can hook systems together to do interesting things is what's called a parallel connection, and I think it's pretty easy to see why they're in parallel. You have 2 systems here that run parallel to each other. There are a couple of conventions here we need to talk about. I want you to notice here that I have x coming in and it gets split. At least that's what the diagram is seen to indicate. In system theory, the convention is that when such a split occurs, it doesn't mean split the signal in 2 or anything. What it means is the same signal is applied to both systems after the split. So it's just a convention. That's why I labeled this very carefully x of t. When we get to talking about this in special cases, you're not going to see me write this. it'll be understood that the input to S1 and S2 is x of t. That's what this diagram means. We also have a new system over here. We have a 2-input, 1-output system. And I think it's pretty obvious what it is. It's an adder. So if we were to call this Y1, the output of that system, and that Y2, then Y was Y1 plus Y2. So that's what an adder does. I think it's pretty self-explanatory in the terms of this, what's called block diagram. So a parallel system has 2 systems in parallel, each having the same input x, and you just add up their outputs to produce the total output. So for example, suppose you wanted to model an echo chamber. So in that case, the system S1 would, let's say, do nothing. Its output is equal to the input. The output of S2, or rather S2 would be a delay box. It would delay its input. After you add them together, you get the same signal plus itself delayed. That's what happens when you have an echo. You get a signal plus its delayed version. So I could construct something out of very simple systems that's a bit more complicated. Okay, finally, we have the most complicated structure that we're going to encounter, the feedback. And I'll explain how it's used in a second, but let's go through this. So we have the input, and there's the output. The input is going to go through an adder, and the other input to the adder comes from something derived from Y. So the way we think about this is that this output of this adder is an error signal, because you can see this little minus sign sitting here. Well, that's the standard convention, which means that the E is equal to X minus the output of S2. So that little minus sign right there corresponds to that minus sign. So that's how you indicate a difference instead of a sum. So what this feedback configuration does is it takes E, passes it through S1 to produce the output. But that output gets fed back through S2 to occur at the input. That gets subtracted from X and produces the error signal, which goes round and round and round and round. So this is the way a cruise control works on a car. You may change the setting for the velocity at which you want the car to go, and if that is different than its current velocity, that produces an error signal. That causes the engine to rev. Let's say that describes the engine, causes an output velocity y, but that goes through the control system S2 to produce the error signal. And finally, when the error goes to 0, the cruise control kind of settles down and doesn't accelerate the car anymore. So that's a great example of a feedback system. I want to point out that everything I just said in that example wasn't electrical. Turns out systems can describe a very general class of signal. The fundamental reason is they're just mathematical constructs. And system theory and signal theory, for that matter, applies to electrical signals and beyond. So it's interesting that you can use these kind of models to describe much more general things. All right, let's talk about special cases, special systems. And perhaps one of the most important are linear systems. Let's look at this. So we have a system S. If it is linear, if you take an input that consists of a sum of inputs, sum of signals, so x1 is a signal, x2 is a signal, and a2 and a1 are scalars, constants. The output to that sum is the sum of the outputs to the simple signals. So if you put in x1 by itself into S, you get that for an output. Put in S2 by itself, you get that. You add those two together with the weighting constants, that's the same as if the system saw this sum presented to it as an input. So this is a very important property of linear systems. It's called the principle of superposition. We're going to use this a lot. We've already seen, when we talked about signals, that it's very convenient in many ways to think about signals as a sum of simpler signals. So for example, that triangular signal we saw in the signals video, we wrote as a sum of 3 signals. Well, to find out what the output to some system is to that signal, all I have to do is figure out the output to a step and to a ramp and a delayed ramp, add them all up, and that's going to be output to our complicated signal. So this principle of superposition is very, very important. It helps decompose problems. Once you can decompose a signal into simpler parts, you now can find the output because you probably can easily find the output to a simple signal. So here's the some special cases of the linear system. Let's assume that the linear system here, S, is linear. If you multiply the input by a number, you change its amplitude, well, the output is going to be the output you had before multiplied by the same gain factor. And there's a way, almost sloppy way of saying this: you double the input, you double the output. If that happens, then the system could be linear. If that does not happen, if doubling the input does not double the output, then the system can't be linear. It violates the rules. That's a special case of what I wrote up here, because here we have A2 is 0 for the case that I'm showing down here. Okay. Then the other case is just as I described in some detail. If you just decompose a signal into a sum, its output of the system, that the system's output to that sum is the sum of the outputs to each. So that goes just to the detail of what we said before. But this result, turns out, has a very interesting consequence. So let's consider a special case. A2 is the negative of A1. And let's say that x1 and x2 are the same thing. We're just going to call that x. So A1 and A2 are negatives of each other, and these two signals are the same thing. Well, what that gives us is that the input to our system is A1x minus A1x. Well, that's called 0. But now, let's look at what the linear system equation says in that special case. Since x1 and x2 are the same, we have s of x, and then they're weighted by the same A1, but they're subtracted to get 0. So if the system is linear, you stick in 0, identically 0, into a linear system. What you get out is 0. Any system which doesn't obey that rule cannot be linear. So if you stick in 0 and the output is 1, that system is not linear. It's sort of a very simple test, but it's not what's called sufficient. It's a necessary property, but not sufficient. The real test of whether something is linear or not goes back to the original definition. And by the way, in detail, this principle of superposition has to apply for all signals x1 and x2, and all constants a1 and a2. So it's a pretty demanding requirement, but when you have a linear system, it's very, very nice. Now, another special class of systems are so-called time invariant systems. So what these kind of systems are is that if you come into the lab, let's say, and you build a device and you put in an input and you measure what the output is, you leave the system alone, you come back the next day, you put in the same signal, And what you should get out is exactly the same output as you had the previous day. And that scenario I just described means that I delayed the input to the next day, and what happened? I got out that day the same thing as what I got the previous day, but delayed, occurring the day that I do the measurement. So systems that do not change their behavior with time are called time-invariant systems. That does not mean that signals can't vary with time. That's certainly not the case, but it does mean the system doesn't change its behavior with time. It stays the same. So let's go through a little set of examples and see if we can figure out how to classify signals according to whether they're linear or time invariant. So here we have the gain box. Multiply a signal via an amplifier. Let's say G is bigger than 1 and positive. It's an amplifier. Is that linear? Well, if I change x to x1 plus x2, do I get G times x1 plus G times x2? I certainly do. It's linear. Is it time invariant? Well, I think it's pretty obvious that it is. If I just change t to t minus tau, what I get is the previous expression for y if I stick in t minus tau there. So this is linear and time invariant. No problem with that. Okay, another example. How about the derivative box? Something that takes a derivative. Is that linear? If you take the derivative of a sum, is that the sum of the derivatives? And I think you'll agree. Yeah, sure, that's true. So that's linear. How about time invariant? What's the derivative of x of t minus tau? Well, that's in calculus you learn that's the derivative of x evaluated at t minus tau. Well, that makes it time invariant. So that's we've got two special cases here of linear and time invariant systems. How about this system? How about the squaring system? So the output equals to the input squared. Well, that is certainly not linear, right? Because the square of x1 plus x2 is not equal to x1 squared plus x2 squared. So that is definitely not linear. How about time invariant? If I replace t by t minus tau, is that the same formula I get if I replace t minus tau in this relationship, input-output relationship? The answer is certainly is. So this is an example of a nonlinear but time-invariant system. And finally, how about this system, which is called a modulator? So what we have is our input is here, and what happens is that the system multiplies it by cosine 2 pi fct to produce an output. Well, is it linear? So if I have x1 plus x2, do I get out cosine x1 plus cosine x2? And I certainly do. So that's linear. How about time invariant? So the thing to notice is that the delay applies only to x. So if I replace x here by t minus tau, you don't replace it over here because that's inside the system. That's not the input being delayed. Well, that's not the same expression that you get if you replace t minus tau over here in this formula. You'd have to replace the t in both places by t minus tau. So this system is not time invariant. You delay the input, you do not get the output you had before delayed because this cosine is changing behavior with time. So we have the cases where go through these examples. You can have systems also that are not linear and not time invariant, of course. And the ones that are really going to be special are the ones that are linear and time invariant. We're going to have to deal with this one, but we clearly can't use the linear time invariant system theory to talk about it because it is not time invariant. We'll see that in a second. Well, okay. We now know a lot about systems. What systems do is they operate on input to produce an output for some reason. You might want to amplify it. You might want to delay the signal, take its derivative, whatever. That's what systems do. They can do all kinds of things to signals that are interesting, and by building up structures of simple systems, you can make something that's a lot more complicated than any of the components. And that's basically the way electrical engineers do a lot of design. Break down a complicated input-output relationship into a simpler set that I can realize by cascade and parallel and feedback structures if I can. And I keep emphasizing that linear time invariant systems are very important. What we're going to call LTI. LTI systems really are important. They occur a lot. And as when we see, when we start talking about circuits, we're going to talk about linear time invariant circuits. When we get to signal processing, I'll talk about linear time invariant signal processing. Those special systems are very important because you can do a lot of very interesting things and have a very good theory for them when we start talking about them. That comes very soon.